Hello everyone. It's my great honor to be here, and today the title is AI-empowered digital twin for traffic safety analysis. And here is the outline for today, which has four components: the introduction, framework, components and methods, as well as some conclusions. So we know that nowadays the road transportation system worldwide has faced a persistent safety challenges, and even nowadays we have around like 1.3 million lives lost annually, and especially in United States, we have over 40,000 fatal crashes occurred in 2023. So to be honest, the traffic safety domain has been well analyzed for several decades. There's lots of efforts have been paid, but the traffic safety still remains a very huge challenging. So there are actually four critical challenges in the crash preventions. The first thing is the traffic crashes, rarity and randomness. As you may know, that there's lots of crash data, but still, due to the nature of the rarity and randomness, we know that the probability of the traffic crash is around like uh, tens to the power of -9. So which means that there's only 1.25 fatalities over 100 miles. So this rarity natures really prohibits the analysis of the crash preventions, and especially we also know there could be randomness inside the traffic crashes, which makes the task more even challenging. So another challenge that we have in the crash prevention is the human behavior, or we call context sensitivity. As we know, in the first class of the transportation engineering, we know that the pedestrians, drivers, as well as infrastructure will co-interact with each other. Well, there's no such a model. So that's why nowadays analyzing the crash prevention, considering the human behaviors, especially with context, is really prohibitive. And the third challenge is that we know there could be a group dynamics, which means that there could be a high order graph dynamics among the pedestrians, vehicles, and environment, which makes the challenges very pronounced. And last but not least, we have a limited high resolution data for validation. Even the crash data set are very available for different DOTs, but usually this macroscopic crash data sets only provides like a very broad coverage, just document different categories, but it lacked detailed context. Well, if you want to do the very detailed analysis from a microscopic manner, they lack those high resolution trajectories as well as vision data. And this leaves the safety models with abundant routine driving data, yet insufficient to validate the crash mechanism. So given those challenges, so nowadays in academia, there are two types of method to analyze the traffic prevention. One is passive safety, which we know is crash data, crash report data set based. Usually is historical and time horizon aggregated, as well as factorized based. Well, for the active safety, we usually believe it is risk-based, preventive, microscopic, and behavior-based. So even though, the active safety have been widely discussed, there's never a formal definition of active safety. So in my personal perspective, the active safety describes the human intuition based on our daily traffic routine in a quantitative manner. So for example, so if you travel on a road, even you know nothing about whether there's a crash happened before or not, you still kind of have the feelings whether the road is safe to travel or not, right? So So essentially, the active safety try to quantitatively measure those intuition. So nowadays for active safety, so due to the data limit, as I mentioned, so rather than learning the crash reports, it many focus on keep adding physics fidelities or leverage the potential AI to capture the potential of risk rather than the risk itself. Let's look at what have been analyzed so far since 1975, which is the first time to collision was proposed. Though even 4 decades have passed, I should say that nowadays the surrogate safety measures is so related to time to collision, while the design philosophy is really simple. It simply assumes that a vehicle remains a constant speed, and usually those time to collision metrics can only be applied to one-dimensional or piecewise one-dimensional traffic scenarios. As I also mentioned that the current surrogate safety is context insensitive. So in this sense, what we are trying to do is to extend systematically and fundamentally active safety analysis with theoretical approximation together with digital twin and advanced AI technique. And we aim to build a new platform, essentially the digital twin approach that's generic to all kinds of highways to provide the essential context. And we also aim to develop a comprehensive analysis tool to capture the high-order vehicle dynamics by physics, which could be directly related to the vehicular control. And last, we aim to provide the emerging AI to further bestow the prediction capability to current active safety analysis. So then let me further move on to the framework. So for today's lecture, I will further cover the digital twin-based transportation system constructions. For example, the traffic background generations, as well as a joint simulation tool developed by my team. And then I will further move on to the high-fidelity stochastic safety analysis, the new method. Last, I will talk about some AI tools to predict the trajectories and embed it in the active safety analysis. So for the digital twin that we developed, that we harness the vehicle mounted sensor, essentially the inclinometer, to provide a very detailed slope and sort of super elevations. And we also utilize the drones. Here is the Skydio 2 Plus US-made drones to collect the necessary informations. And we also integrated with the current map of, and we use OpenStreetMap since it's an open source information that everybody can get. So here, let me firstly show you our videos that we use our drones to collect the information necessary for the digital twin. And this is an automatic drone once you define the areas. And then it can automatically collect more than thousands of photos that overlap each other to have some 3D geometries. And then we can readily fit into the reality capture to have a 3D model constructions, and it can finally be output as an area LiDAR point cloud for the use of the simulation. So given that we use the OpenStreetMap as a skeleton, while the area LiDAR point cloud as a flash to give the comprehensive scenarios of the traffic static background. So by the OpenStreetMap, that we can provide the type of road, for example, whether it's a motorway, trunk, or primary, as well as the surface, lane, so on and so forth. And for the area LiDAR point cloud, we use the state-of-art method for the semantic segmentation by the render net to get the lane width, curvature, vertical alignment grade, so on and so forth. and then we can readily convert it to a road runner that can be readily used for the simulation purpose. So here I just provide an example to demonstrate that given those roadmaps, we can readily output all kinds of geometries from the road. For example, the vertical grade, cross-section grade, as well as a curvature. And we further validate the maps or the background with vehicle multi-sensors as the ground truth, and we find that the accuracy of the digital twin generated by this multi-view photos and the OpenStreetMap is very decent, and errors only occurs at the boundaries of the map due to the photometry AI applied in the system. So given the background, what we are going to do is we want to put the vehicles inside, and specifically we want the vehicles to have a very high fidelity physics. So that's why we developed these joint simulation structures, which have three components, sumo, color, and physics X. So if you are in the simulation, you are a simulation guys, you may know the sumo and color code simulation developed by UCLA recently. But the gist here is to provide a physics X provided by the NVIDIA to capture like a road, the vehicle skidding, rollover, go off the road, more complex scenarios that fail to be generated by the existing traffic simulation tools. And for sure, there should be some synchronizations among those three tools, then we can fulfill the joint simulation in real time. And here is a simple demos of the Sumo and Kala. So essentially, you can use the Sumo to generate the traffic control device and basic, traffic. Well, and further in the Kala, that you can always pick different cars, trucks, vans, bus together potentially with the tire frictions, mass damping system, so on and so forth, enabled by the physics X. And furthermore, you can even customize the mass of the vehicles, the center of the mass of the vehicle. For example, if I really care about the freight safety, right? So for the trucks, then the center of mass will come into play. And this NVIDIA physics engine provides a very, very detailed vehicle dynamics that has not been captured by existing traffic simulation. So here, I will just provide some very simple demo to show that, the first case is that the tire friction is enough. All right. And by this NVIDIA physics X, you can even get the tire force as well as the wheel information in a real time. Another example is that the friction is not enough. For example, the snowy condition, raining condition, so on and so forth. Then you'll see the skidding phenomenon of the vehicles, which is never captured by the existing traffic simulation, I should say. But there could be lots of vehicle dynamic scenarios here. I just provide some examples to demonstrate the capability of the joint simulation platform. So given those simulations, then we are more interested in the analysis component, and we call this as a high fidelity analysis tool. And the first thing is that we develop a theoretical foundation for the 3D dimension high fidelity surrogate safety measures that can incorporate as much complex vehicle dynamics as you want. And given that, we further do some behavior calibration that we can embed it in the tool to put inside the active safety analysis. For example, here, the cutting analysis for the commercial AVs, or we also can do human-driven vehicles for sure. And we know that active safety analysis usually is based on the vehicle perspective. Then we further utilize the extreme value distribution as well as the hierarchical Bayesian learning to convert the vehicle perspective to a location-based perspective to cater to different stakeholders. For example, the vehicle manufacturers is vehicle-based active safety analysis, right? But for the government, usually they want the location-based perspective. But for today, I'll just quickly go through some techniques that we developed. And many pertains to the philosophy level. So we know, right? So for the every motion can be described by an ordinary differential equation. So that's how we do it when we shoot the satellite into the sky, right? They are all developing this tool. So essentially, every vehicle motion can be formulated as a nonlinear ordinary differential equation that has a function, which is a function of the vehicle state. We use x sub it for the vehicle I, as well as UIT. So essentially, the state could be the position, heading direction, vehicle velocity, depending on your fidelity needs. And based on that, we can analyze any vehicle-to-vehicle clearance, for example, vehicle I to J, given a generic clearance functions, or even vehicle-to-road or vehicle-to-obstacle clearance functions. And given that, we say that if there's a non-negative solution exists, and the earliest one indicates when the vehicle will collide. So this is quite like a mathematical, but here I would like to give you some equivalents that you can directly link to the traditional surrogate safety measures. So for example, if you like the vehicles to be the state to be the position, and you like the control input to be the speed, which remains a constant, and the general clearance functions is a position offset minus the vehicle length, then you can directly get the traditional time to clear. Or you can even do the second order vehicle dynamics, and you can get some like acceleration related surrogate safety measures. But what I should always say is that the thinking itself matters. So given this ordinary differential equation formulations, this framework is essentially generic. You just use a different perspective to find a surrogate safety measures, right? So essentially finding a high fidelity surrogate safety measures equals to solving an ordinary differential equation, I should say. The law is very simple. And depending on the fidelity need, as well as the availability of parameters, you can always find out the corresponding ordinary differential equation. So which will be really helpful if you use, for example, the NVIDIA Physics X with a 16-degree of freedom vehicle dynamics, you can still get a surrogate safety measure in a very, very high fidelity manner. As well, one thing I should also note is that the control input should be a behavior function, can be a behavior function of X. So if you want to put inside some behaviors inside the surrogate safety measures, you'll be good to go. And here, I just provide a very simple demonstration that we consider the 2D motions of the vehicles with 3D dynamics. For example, we consider the gradient, and we can still get the surrogate safety measures out. So here is something that I would like to share is that if you use the traditional time to clear, you will always get some overestimate of the time to clear by 300%. if the prediction horizon is very long, for example, 6 seconds, and about like 20% when the prediction horizon is 1.5 seconds. Okay. And we also, use some like demonstration to show that this ODE, solving ODE can be readily computed in a real time. So given that, we also do some like behavior calibrations. For example, we use AV test from the Massachusetts, funded by the NSF, as well as some Waymo data set to capture the behaviors of the current existing adaptive cruise control. We get the parameters we feed into our systems. And then for here, it can also help you to make a decision. For example, I know that I have adaptive cruise control. At what scenario I should overtake, at what scenario I should yield, and at what scenario I'm safe to karting. So it can provide lots of insights here. And another thing is that sometimes there could be stochasticity in the systems, and we also want to do some like a stochastic extension based on the unmodeled uncertainty in the either vehicle dynamics or uncertain area. So essentially, we represent it by stochastic differential equations. And here, I'll just with some like a winner noise treatment. And again, it's very, very similar to solve a stochastic differential equations, and then you can find out the cumulative density function of the time to clean, so on and so forth, or even use a Monte Carlo simulation. So we did some like a very analytical magic. We use a KBE, and what we prove is very simple story is that if you want to get the cumulative density function of the stochastic high-fidelity time to clean, you only need to solve a parabolic partial differential equation, which is readily solvable by current existing solver, for example, finite difference method. But as I said, I'll just skip the mathematical details, just tell you the story. And given that here we just demonstrated that this time to clear framework can be applied in like ground vehicles as well as the potential flying vehicles and gives you the cumulative density functions. But most importantly, this analytical approach can reduce the computational time by 99 and 98% with respect to the flying vehicles and ground vehicles compared with a Monte Carlo simulation to fulfill the digital twin real-time computation need. All right, so given that, right, so we have the very high fidelity vehicle dynamics, and we sometimes, it's only for the targeted vehicle analysis. Sometimes we also want to incorporate the ambient vehicle's behavior inside our surrogate safety matters. So that's where the vehicle motion prediction comes into play. And so specifically for this approach that, we focus on the basic philosophy is that we know in the traffic environment is very complex. We have vehicles, vulnerable road users, as well as traffic control device. So essentially, we treat it as an agent or node. And we know there could be interaction, model as edge. For example, there could be same type of interaction, essentially vehicle-to-vehicle interaction or cross-type interaction. For example, the vehicle-to-road interactions, which requires us to have a heterogeneous approach. And specifically, we know that the traditional graph approach is to model the pairwise interaction. But in the real world, the vehicles may have a group-wise interaction that's much beyond the pairwise interaction. So that's why we use a hypergraph as a natural extension of the traditional graph. And the hypergraphs, the edge can connect to any number of nodes, not limited to one. And it essentially is a high order graph dynamics in the graph theory. So, and by different scales, for example, if the scale equals to 3, which means the edge can connect to 3 nodes. For the scale 4, the edge can connect to 4 nodes. So this is much beyond than a traditional graph whose scale is 2. And this hypergraph approaches provides more like flexibility and generalizability to capture the group-wise interaction. And furthermore, we consider the multimodality of the behavior. For example, the way that how I drive could be totally different than the emergency happens, right? We consider this multimodality of the behaviors, and we can further consider in the multi-lane case, for example, once there's a lane change, car following or merging, this can introduce like a graph structure change. So we use a hypergraph learning based on the NGSIM data set as well as the HIDE data set. And this approach can provide a probabilistic trajectory with relationship reasoning. And furthermore, by comparing with the state of our methods, we find that it can provide very, very accurate trajectories prediction by capturing this high order vehicle dynamics in a group-wise manner. So here is how we combine what we develop here. So given the host vehicles, then we can have a very high fidelity vehicle dynamics, and we further input the predicted vehicle trajectories inside these surrogate safety measures. By that, we can analyze our clearance based on our digital twin platform. So here is an example in our systems that we develop to analyze the active safety in a real-time manner. So essentially, the blue one is a ground truth, and these like blue lines are predicted trajectories, and this like a black interface shows the vehicle-to-vehicle clearance, time to clear. So essentially, but it's in a high fidelity manner rather than the traditional time to clear. So let me firstly summarize the component for this part. So initially, we have some certain level of safety standards, and we know it is called as the Green Book, right? Yeah, in the Green Book, we assume some vehicle dynamics, but very standard one, and we do our highway and infrastructure design. But for our tool, we actually did in the inverse process because we know that there could be aging infrastructure, there could be bad designs. Firstly, we use our sensors to monitor the traffic background, and then we input with very high fidelity vehicle dynamics to conduct the active safety analysis. So nowadays, especially, we will have the generative AI, or we have large language models, right? So the question is that, can we really leverage those generative AI in the field of active safety analysis? And here is some like work that I participate. And what we do is that, firstly, we have the NISTA crash report, right? And we use a large language model to change the reports to the text description. For example, what's the lighting conditions, what's type of the clearance, so on and so forth. And we put into the war models, for example, Cosmos. And then we evaluate the physics groundings of the world model. For example, whether it is follows a physical laws, momentum or energy consumptions, or whether there's an ID switch, so on and so forth from the V side. And we also do the same thing in the simulator. And by that, we combine those two together to fine tune the world model to see whether, it can generate some traffic crashing scene just by the Nishta crash reports. And here is a demo shown here. We all find out, it looks very, very same. And we check, by the fine tune, the physical groundings will improve. But I still need to comment here is that if you use a world model, it's not that controllable, to be honest. So for example, if you are designers, I want to install a stop sign there, or I want to adjust the light conditions, so on and so forth, right? So if you are like a traffic designers, it's not as controller as we imagine. So that's why nowadays we're developing a agentic system for the simulation. So for example, as I shown to you that the joint simulation, right? We have a Sumo, Kala, NVIDIA Physics X, really hard to use, or only us know how to use it, right? But if we want everybody to use it, the US DOT to use it, traffic engineers to use it, it takes months for the software training, right? So it's very, very, has lots of hurdles to be used. So that's why we are considering now, how about we use a large language model agent to help you to do that? For example, there's a chat box, you just type in your need, and then it can automatically construct the simulation, right? And here we provide several scenario generations and some scenario synthesis, all enabled by the code agent. And this can greatly help us to augment the crash data set with certain level of physics plausibility. And this approach is more controllable to provide the countermeasure insights, right? Because everything is controlled by coding agent. So I should say this like a coding agent or digital twin agent is still under development, but we do have some preliminaries for the, even integrated with the V2X stuff. And here, the blue line in the video shows vehicle to infrastructure communication, and red line shows vehicle to vehicle communication. Basically, we just provide the information flow. And if we say, hey, I want a daytime urban traffic, arterial traffic, and it can automatically generate some traffic in our digital twin platform. But for this case, it's only in color. And here's another case for the congested traffic on the raining condition with degree visibility. Very similar things. So, but it's still under development, and we try to control every simulation needs into agent so that we can readily control everything and to do lots of data augmentation in an automatic way. So that's all for the presentation, and this research is partially supported by Federal Highway Exploratory Advanced Research, Texas A&M Data Science Career Initiation Fellow, as well as NVIDIA Academic Grant Award. And I'm happy to answer the questions. Thanks so much.
So, okay. Maybe I can raise the first question. So I'm just wondering for the simulation that platform that you construct or develop. I mean, because you consider many detailed operation, right?
Yes.
So I'm just wondering how large scale it can simulate.
Yeah, thanks so much. That's a very great question. Now we test even for 1,000 vehicles, relatively large networks, it works out in real time.
In real time,
Yes,
thousands
of vehicles.
and how.
But the thing is that you need to have a NVIDIA 5090 GPU first, but it's not expensive, $3,000. Be good. But you need to have a GPU to run this high fidelity simulation.
And
That's
what the
network size, intersection wise, 30 to 40
30 to 40
intersections together. So the network contains 30 to 40 intersections.
So actually, it's gonna be scalable, right? If you have more advanced GPU, kind of like that, you can.
Yes, the answer is yes. But we even with very like a 50-90, then you can still do 30 to 40 intersections. But you want to do let's say New York City, very microscopic with all vehicle dynamics. Actually, I don't know. I don't know the result. I haven't tested the scalability, but small network, thousands of vehicles, it'll be fine. It'll be fine. But if you have a Blackwell, stations, for example, NVIDIA just donate my team some Blackwell stations. I believe you can run like more than 10,000 vehicles. Yeah.
You already have a very great physical environment, but you want to examine the risky scenarios based on the human behaviors. So how can you identify those real behaviors based on limited data?
That's a very good point. So that's what I say, right? So due to the lack of the data, right, especially high resolution, context-aware data, every surrogate safety measures cannot be that accurately analyzed. So that's why now in safety area, we focus on the near-miss events. But once you have the digital twin or even automatic agent digital twin, right, then you can further try to analyze the crash on the condition what if, right? Because the what if matters. So for example, even for this role, right? For today, you'll be fine. But what if now there's lower visibility? What if there's like a skid, the coefficient is not enough? But if you have the agentic digital twin, then you can begin to explore and say, what if, right? What if, and then the near miss could be real crash. But the first thing is that we need to firstly have a agentic digital twin. So that's what we are working on actually, right? Yeah, but once you build the connection of the near miss to real crash with a what if condition, then you can do lots of reasonings, the countermeasures design, so on and so forth. But now we cannot do that. We can only analyze the near miss due to the limit of the data, right? So if you check the trajectory data set, even you try to find out the crashes, for example, the Argoverse 2 provide like a crash, like a AV trajectories. There's only 2 crashes, right? It's really, but if you just try to validate your framework with 2 crashes, it means nothing. Yeah, but that's a very insightful comment. Thanks. And one thing I would like further highlight is that this like curse of rarity, traffic crashes. So if you treat the crash as a binary process, for example, the probability whether it's crash or not, right? It's like a binary like stuff. And if you try to, if you use try to estimate the feature informations or relative standard errors of the estimation, you'll find out that, right, even with a very huge data set, the estimate could be really noisy due to the very small probability, 10 to the power of -9, right? So which means that with the existing AI tool, no matter how you do it, you always yield noisy estimates. It's basically trying to find a needle in the haystack, right? Super hard, right? So that's why we propose we should learn what didn't happen, and we should learn what if conditions, right? Basically, you can augment, because near miss probability is much higher, right? So if you can build a link between the near miss, so firstly, you estimate near miss, you can get a very high, relatively high, estimate, accurate, higher as the estimate with higher accuracy. If you can build a link, then you are more close to understand the essence of the crash, not in a correlation manner, but in a consequential and causality manner. So that's why we need to have those tools.
So for the counterfactor features, which part do you think is more important for the agents? Like, we should put them in the training process, or we should just put them in the execution process? Which part is more important?
I should say both.
Both.
Yes. Yeah. Counterfactual learning. You can also treat it as a reinforcement learning, right? To generate the scenarios with a higher risk of crashes.
Yeah, I just want to mention, I mean, Henry published the paper, right? Few years ago to generate those high risk scenario, right?
Yeah, but mainly for the behavior wise, I should say. If you check the paper, it says, hey, what if the vehicle make a cutting condition, so on and so forth. It does not have the dynamics, right? Speeding, rollover, all the stuff. No. And the beauty is that the behaviors of the truck and sedans could be different. Vehicle dynamics could be different. Even their vehicle design is different. So that's why we need to have, first thing, generic framework. Second thing, high fidelity vehicle dynamics platform.
Sorry, another question. So like when we human beings driving, we don't have those accuracies or high dense data from our perspective, but we still can drive well. So now we have a lot of different sensor capture different data. Why can't those agents drive it better than?
Actually, if you really check I don't know whether you drive the Tesla FSD, right? If you try Tesla FSD, I just share, it doesn't mean any like a public perspective. I just share my personal perspective. It drives better than the human beings. FSD, if you try this version, for example, I from College Station to Houston usually takes 1.5 hours. I have no need to intervene at all, even for the round trip, no. Because so basically it's like they have tons of the data from Tesla, and the cameras are all well mounted. All the sensor parameters, the location parameters are fixed, right? They use end-to-end training. The beauty of AI is that if the large data set, if the data set is large enough, if you have enough computing power, then you can always find a very, very good driving policy, and it's better than human. That's how I believe it. So, but also personal experienced. So so that's why, I partially disagree that, now AV can drive really, really smart. Thanks so much.
Thank you. Much. Yeah. Thank you.
Thanks. What should I stop sharing? Oh, there's questions from audience. Oh, no. Oh, okay.